Hi guys. So today we're going to talk about approaches to proving the Cauchy-Riemann equations. And I'll tell you that basically the proof of the Cauchy-Riemann equations comes down to using ideas of linear approximation that we see in multivariable calculus. And in particular, the mean value theorem shows up. Now, the argument in Johnston skips a lot of steps in the converse direction. So I want to do a little bit more to indicate how the ideas that you apply there work. But essentially, this is one of the most beautiful applications of multivariable calculus that you can have, is to generate a condition for analyticity in complex functions. And again, this supports the idea that that complex analysis can be viewed as an extension of real calculus, in this case, two-variable calculus. So the first thing we're going to do is we're going to try to show that if we have a differentiable function f, and recall that differentiable means analytic in the complex setting. So once complex differentiable implies that the real and imaginary parts satisfy the Cauchy-Riemann equations. So throughout this argument, we're going to write down, so throughout, we're going to write z as x plus iy, so real and imaginary parts of z. And we're going to think of f of z as being equivalent to f of x plus iy, which we can think of as decomposed into real and imaginary parts. So a u of xy plus I times v of xy, where u and v are real valued functions. So from R2 to R. So u and v take R2 to R. Another big assumption in this argument is that u and v are functions that have continuous derivatives. And so through the arguments, we have in both directions, we're starting with u and v both having continuous first partial derivatives. So another assumption that we make throughout is that u, v, ux, uy, vx, and vy are continuous throughout some disk, right? Okay, so with those assumptions, let's see if we can actually prove the relationship between differentiability of f and satisfaction of the Cauchy-Riemann equations. So recall, I guess maybe we can write the goal down really fast here. So the goal is that we want to show f complex differentiable at z is equivalent to ux being equal to vy and uy being equal to minus vx at z. And when I say at z, I mean in the complex differentiable sense, so in a neighborhood. All right. So the easy direction is to show that once differentiable implies that the Cauchy-Riemann equations hold. So let's assume that f is complex differentiable at z. And I'm going to remind you that when I say complex differentiable, I mean in an open disk centered at z. Now, what that means is that f has a convergent difference quotient. So that is to say that f prime of z exists and is equal to the limit as h goes to 0 of f of z plus h minus f of z over h, where f is contained in some sort of neighborhood that's approaching well, basically, the idea here is, I guess, that there's a lot of ways that you could approach z. And so you think of h as being contained in some little disk around z. What we're going to do is we're going to play the game that you may have seen in calculus of two variables, where we're going to pretend that we're going to restrict our attention to just very specific approaches. So we're going to let h be a real number and approach along the real axis, and we're going to let h be an imaginary number and approach along the imaginary axis. And the reason this works is because we already know going in that f is differentiable. And so the limits as we come in from any direction must be the same, because f already is assumed to be differentiable. So the first thing we'll do is we'll assume that h is a real number. The picture here is something like if this is z, and we have some disk around z, we're going to approach z along the real axis. So h is assumed to be real here. In that case, we can write down the limit as h goes to 0 of f of z plus h minus f of z over h. I'm going to rewrite this in terms of real and imaginary parts of z. So I have f of x plus h comma y, because after all, maybe I should be a little bit careful here. Let's be slightly careful. I'm going to think of this as f of z, x plus iy plus h minus f of x plus iy over h. But since h is real, I can lump it in with the x, and that gets me the limit as h goes to 0 of f of x plus h plus iy minus f of x plus iy over h. And now I can cut f into its real and imaginary parts, which gets me the limit as h goes to 0 of u of x plus h. Should be slightly careful here. Y plus I times v times x plus h comma y minus u of xy minus iv of xy all divided by h. And these are just expressions for the partial derivatives. This is the limit as h goes to 0 of u of x plus h minus u, sorry, keep skipping out variables here, comma y minus u of xy over h plus I times v of x plus h comma y minus v of xy over h. And because u and v have first partials that exist, I'm just allowed to evaluate these limits. This is an expression for ux. Y. And this is an expression for vx. That's what those difference quotients measure, is the x partial derivatives of both of these expressions. So what we've shown is that f prime of z is equal to ux, x at xy, plus I times vx at xy. If you run the same calculation, but now we let h, but the h going to 0 approach along the imaginary axis instead, we could write down the limit as IH goes to 0, because now we have an imaginary number of the same exact computation, right? So f prime of z is equal to the limit as IH goes to 0 of f of z plus IH minus f of z over IH. And if you run that calculation through, using exactly the same idea as we already did, what you'll result with in the end will be Vy of xy minus Iuy at xy. So the same computation, but now with this limit. If you substitute in and you replace f with its real and imaginary parts, u and v, and you resort things and look at difference quotients, you're going to get instead the expression Vy minus Iuy. Now, since the derivative exists, these must be equal to each other. This is equal to f prime of z, and this is also equal to f prime of z. So f prime of z is a unique number that exists. So if I have two different expressions for the same number, they must be equal to each other. So it must be the case that ux plus ivx is equal to vy minus iuy everywhere that the function is differentiable. And so equating real and imaginary parts of complex numbers gets us that ux must be equal to vy and Vx must be equal to minus Uy. And these are the Cauchy-Riemann equations. And moreover, we get the powerful sort of computational tools for figuring out what the derivative of a complex function is from its real and imaginary parts. So also, it's important to note we get for free that f prime of z can be written as ux plus I vx, or if I like instead, I could write vy minus I uy, which are useful computational formulas. All right, so the other direction is the tricky direction. This is a pretty straightforward computation involving difference quotients. Again, to reiterate, notice that all we've done here is regular old two-variable calculus in real variables. There's nothing else here except for stuff we already know about difference quotients of functions that have derivatives. Hi guys, so this is my probably fourth attempt at making this argument. So what I want to talk about is the converse direction of the theorem that states that complex differentiability is equivalent to the real and imaginary parts of a complex function satisfying the Cauchy-Riemann inequalities. And part of the reason why it's so hard to explain this is because it's not a hard argument, but there's a lot of moving parts. And so what I'm going to do is I want to remind you of a couple of ideas from calculus that we're going to use in this argument, so that when I assert them, that it's not something that is mysterious. So the first theorem that we want to use is the idea called the mean value theorem. All right. So what the mean value theorem says is that if you have a function with a continuous derivative, so if f is a function and f prime is continuous, then f of b minus f of a is equal to f prime of c times b minus a, or some c inside the interval from a to b. In a picture, essentially what you're saying is that if you have a continuous function, continuous derivative, and you have an endpoint b, and you have an endpoint a, and you calculated the slope of the connection between those points. This is f of b minus f of a. And the slope of that line is f of b minus f of a over b minus a. So it's the slope of that line, that somewhere in between a and b, there's a point c. So maybe that's c. So that the derivative of f at that point, f prime of c, is equal to the slope of the line that you get by connecting the endpoints. So you learn this in calculus, you don't get the idea that it's an important theorem at all. If you've seen some proof-based analysis, you come to the understanding the mean value theorem is one of the most important tools that we have available. And the reason that's important is because it allows us to take expressions like f of b minus f of a and replace them with expressions that involve the derivative. So it's a way to allow us to approximate a function using the derivative, which is frequently a very useful thing to be able to do. We're going to use the partial derivative version of this. And the partial derivative version says the following. If you have a function, say, u of two variables, so say you have u of x and y, and maybe you increment one of the variables, so you slide by delta x, for example. So we go from uxy to ux plus delta x y. So we slightly increment the x variable. Then the change that we undergo in the height of the function, so we have u of x plus delta x y minus u of xy, turns out to follow the same rule. There's a mean value theorem that applies to each individual variable in the function. So u of x plus delta xy minus u of xy, you could think of as being a change in the height of the function. That's what we're trying to measure. And that change in the height of the surface this function is producing can be approximated by the partial derivative of u with respect to x at some special point ux star of x and y times delta x. So delta x is the same as b minus, where does the delta x come from there? Well, if one of the endpoints is x plus delta x and the other one is x, and you subtract, so the sort of b minus a part from this theorem is x plus delta x minus x, which is delta x. So the b minus a part is right here. Where's the derivative part, this f prime of c? Well, this is the derivative. It's an x derivative because we've slid in the x variable. And so this is the mean value theorem. It's the single variable mean value theorem applied in a multivariable setting. And the last thing we need to say is that this x star value must come from the interval from x to x plus delta x. So the mean value theorem gives us a way of approximating these sort of differences with partial derivatives in the two variable setting. And we're going to use that idea when we're doing the sort of investigation of the Cauchy-Riemann equations and the connection between the Cauchy-Riemann equations and complex differentiation. Okay, so the next idea that we want to talk about is the way continuity of functions links up with limits. So this is all about the mean value theorem, which allows us to approximate functions with derivatives. The next idea that I want to remind you of is the idea of continuity. And the idea is that when a function is continuous, you can push a limit inside of it. If f is continuous, then the limit, say, as h goes to 0 of f of x plus h is equal to f of the limit as h goes to 0 of x plus h, which is f of x, right? A continuous function is a function that you can push a limit inside, is one way of thinking about it. Or that the value of the function is equal to limits that approach that value. So this idea is another important idea when you see expressions like this. So there's an expression that's going to come up in the computation that we're doing that's going to look like u of x y plus delta y. So that's a function of two variables, and there's maybe even be a derivative involved, a uy, say. So this is the y partial derivative of a function u. And the idea is this has to approach u of xy as delta y goes to 0 if uy is continuous. A continuous function respects limits. They go where you think they're going to go. You take a limit of an input variable, and it approaches that input variable, or it approaches the function applied to that variable. If you like, this is just saying that when you take a limit of a continuous function, you can just plug the number in at the end as long as you're not dealing with an expression where you're dividing by 0. Okay, so these two pieces, the idea of the mean value theorem and the idea of continuity, are going to be involved in our proof that a function, if I have a u and a v that satisfy the Cauchy-Riemann equations, then the function we construct out of them must be complex differentiable. Okay, so that's going to be step 2 of this video, is to write that argument down. And I will be very clear about when I'm applying the mean value theorem and when I'm invoking continuity as a property that I need to have. So what is the theorem that we're trying to prove? What do we want to show here? What we really like to show is that if I wrote down a difference quotient that looks like the derivative of f, so what I want to show is that if I have f of z plus some increment in z, and I subtract f of z, and I divide by delta z, I want to show that this converges as delta z goes to 0. Because if it does, it means that f is differentiable, right? If so, it's equal to f prime of z, okay? And that's really the idea here, is that I want to start with a difference quotient and show somehow that properties of u and v are going to allow me to show that that difference quotient can be evaluated as delta z goes to 0, and I get a number out the other side, which is going to establish that the function is differentiable. So what are we going to assume? We're going to assume, as before, that u, v, ux, uy, Vx and Vy are continuous. And for the purposes of this direction, we're going to assume that u and v satisfy the Cauchy-Riemann equations at all z and some disk. Complex differentiability requires that we work in a disk, and so we'll make that assumption. So the first thing that we need to do is figure out a way to take the difference quotient and approximate it with these pieces that we know something about. And in particular, satisfying the Cauchy-Riemann equations means that we're going to have to get partial derivatives involved. Assuming the Cauchy-Riemann equations hold is making the assumption that ux is equal to vy and that uy is equal to minus vx. So that's information about partial derivatives. To get that into the picture, I'm going to have to take this expression and somehow get partial derivatives out of it. That's where the mean value theorem is going to be applied. Okay, so let's begin with our expression, and we'll begin manipulating it. If I have f of z plus delta z minus f of z divided by delta z, and I'm thinking about f as the function that you get by writing down f of z is equal to u of xy plus I times v of xy, then I can use the fact I can break f apart into its real and imaginary parts to write this as u of delta z minus v of delta z. Two functions that are functions just of the variable delta z, where we can define the function u of delta z to be equal to little u of x plus delta x, y plus delta y, minus u of xy over delta z, and our function v of delta z is v of x plus dx, y plus dy, minus v of xy over dz. Right, so it's sort of the real and imaginary parts of the difference quotient. And so to illustrate the method that we're going to use here, let's just concentrate on one of these. So I'm going to start by looking at just this capital U of delta z. And what I want to show somehow is that that converges somewhere. I really want to show that U of delta z goes somewhere as delta z goes to 0. Right. So let's write it out. So u of delta z, which we've already said is equal to u of x plus delta x, y plus delta y, minus u of xy over delta z. I need to get partial derivatives in here. I want to use the mean value theorem, but I can't increment both variables at the same time. I can only increment one of the variables at a time. And so in order to get, I'm going to take this difference quotient and actually turn it into two difference quotients. And in the two difference quotients, I need to isolate it so there's one I can estimate with respect to incrementing in x, and another one I can apply the mean value theorem with respect to incrementing in y. And in order to get those terms in here, I'm going to use what's called an add-subtract trick. So I'm going to add and subtract the same term, but I want to do it in such a way that I get two things I can apply the mean value theorem to. So I'm going to write down u of x plus delta x, comma y plus delta y. And now I'm going to subtract off u of x, comma y plus delta y. And I'm going to add that back in again. And then I'm going to subtract off the original term that I had, which was u of xy. And all of that, of course, is still divided by delta z. This is just a fancy form of the number 0 because I've added and subtracted the same quantity. Now, the reason that we did that is that this looks like a difference in u where we've just moved in the x variables. I moved from x to x plus delta x. That's going to be something I can apply the mean value theorem to in the x variable. And these guys look like a change in the function u where the only thing I've changed is by sliding in the y variable. So I'm going to be able to apply the mean value theorem again in that context. So applying the mean value theorem, one of the first things I can do is I can write down, well, by the mean value theorem, there must exist an x star in the interval from x to x plus delta x. And there must also exist a y star, star, say. Why involve two stars? A y star in the interval from y to y plus delta y. So I'm setting up to invoke the mean value theorem here. This whole piece here can be replaced with ux, x star, the point between x and x plus delta x. And I haven't changed the y variable, so it's still y plus delta y. And then I have to do my b minus a term. So I have a delta x attached to it, all divided by delta z. And that is going to be added to the approximation for this term. Well, that is going to be that's going to involve the y star, because I'm going to replace the increment from u of xy to u of x comma y plus delta y with its mean value theorem approximation, which is uy x y star delta y over delta z. So the mean value theorem guarantees that I can do this. And the other thing to note, this is an equality. Okay, so I don't know where x star and y star are, except that they're stuck in these little tiny intervals. So they're strictly between x and x plus delta x. And so one thing that we must have, and why this is so useful, is that it must be the case that x star tends to x as delta x goes to 0. And also it must be the case that y star must tend to y as delta y tends to 0. Because after all, the x star and the y star are trapped in those little tiny intervals. And as delta x and delta y to go to 0, then those intervals get smaller and smaller and smaller. And anything stuck inside must be approaching the point that doesn't move, which is the x and the y. Okay. So this is our first step, because now what we've shown is that u delta z can be written as this sum of these approximations in terms of the mean value theorem. And now we can do something really cool, which is we can say, well, I mean, these are approximations. And so, and we know that as delta x and delta y go to 0, it must be the case that the x and the y, x star and y star go to x and y. And what else must be true? Well, it must be true that as these delta y's, as this delta y goes to 0, that ux of x star y plus delta y must be approaching y in the second slot because of continuity. So the x star and the y star come from the mean value theorem. And then continuity lets us say that as delta x and delta y go to 0, all of that stuff has to approach ux and uy at xy. Okay. So we're going to make the argument then that as delta x and delta y go to 0, and delta x divided by delta z is less than or equal to 1. After all, delta x, oh, we gotta be careful here. Let me remind you that delta z is delta x plus I delta y. And so we know that the real and imaginary parts of a complex number are smaller than the complex number. So it must be the case that the absolute value of delta x is less than or equal to the absolute value of z, and the absolute value of delta y is less than or equal to the absolute value of delta z. So the fact that these things hold lets us say that what happens as delta z goes to 0 is that we get that ux of x star y plus delta y approaches ux of xy. And that uy of y star, or sorry, of x comma y star must approach uy of xy. Sorry, this is supposed to be v. No, this uy is correct. Have I accidentally written u for? Nope. Nope. We're good. Okay. So the conclusion is that we can write that u of delta z in the limit u of delta z ends up approaching ux of xy. So the idea is that for small delta z, if we we consider delta z to be equal to delta x plus I delta y, that is a small change in complex variables, some combination of a real part plus an imaginary part. If dz is small, that is close to 0, then it turns out to be the case that we get that u of delta z is going to be very close to ux of xy delta x over delta z plus uy of xy delta y over delta z. And that closeness comes from the continuity, right? That because these things are continuous, as the delta z gets smaller, that forces delta x and delta y both to get small, which means continuity gets us that these terms get very close to these terms. So one way, the sort of sophisticated mathematical way to say that is when delta z is small, or in the limit as delta z goes to 0, that we can use this expression instead of this one. And that's just by continuity. That's actually why we require continuity of the partial derivatives, in order to make those things close to each other. Okay, so applying the same idea to v gets us the expression that v delta z is close to, perhaps unsurprisingly, given that you're doing the same computation, vx at xy delta y, that's right, delta x plus vy xy delta y, and these again both are over delta z. Okay, so all we've done so far is just a really straightforward approximation of the difference quotient that we're trying to estimate. So let's check back in and see what we're doing here. So at this point, what we've shown, this is where we are. We know that now that f of z plus delta z minus f of z, this thing that we're interested in showing converges, is equal to u delta z plus iv delta z, and then using the mean value theorem and continuity to get the partial derivatives in, and then get the increments out, we have a very close approximation. So this is about equal to, in fact, we can say equivalent if delta z is small. So for small delta z, that this is equal to ux xy delta x over delta z plus u y xy delta y over delta z plus I times vx xy delta x over delta z plus vy xy delta y over delta z. And we still haven't used the Cauchy-Riemann equations, which means we still haven't used the hypotheses of the theorem. So that's actually what we're going to invoke now. We're going to take this expression and we're going to try to show that, like, as delta z goes to 0, that this actually converges to something. So we don't know that yet. We know that we have this reasonable approximation for capital U and capital V, but we haven't yet shown that we've got convergence. So now invoke the Cauchy-Riemann equations. And the particular place where we're going to invoke the Cauchy-Riemann equations is that we're going to swap out this term, and we're going to swap out this term using the Cauchy-Riemann equations. And so after doing so, what we get is ux xy delta x over delta z, and now uy is equal to minus vx, so this is minus vx, that's a u up there, of xy delta y over delta z plus I times, okay, the vx, xy delta x doesn't move, but vy is equal to ux, so I will replace this with ux xy delta y over delta z. And this is kind of why earlier I said that the Cauchy-Riemann equations are similar to Clairaut's theorem. We're saying something about the relationship between the first derivatives, the first partials in this case. So something about the geometry of the first partial derivatives, the rigidity of the way complex analysis works, gets us this sort of trade. And as cheap as it seems, that trade is what we need to conclude that f is differentiable. Because now I just do an algebraic resort. So I'm going to pull the delta x terms together, or sorry, the ux terms together and the vx terms together. So that's going to get us ux, x and y. And then I have a delta x here and an I delta y delta z here. Plus I times, well, what do we get for the second part? We have a vx, x, y, sorry, in fact, we can even just put that there. Each of these terms, this one and this one, now have matching terms, matching differentials, which are vx. So I can factor that out. I get vx of xy. And what's left over when I do that? Well, I have a delta x. And I have an I delta y. I seem to have lost a minus sign somewhere. Yeah. So there's a minus sign that got lost. That's right here. And so notice here that like the modulus of this number, I mean, that's delta z over delta z, which is 1, right? So this is, if you think about what this is delta z over delta z. And in this term, we get delta z bar. It's the conjugate of the increment of z. And that's divided by delta z. But a complex conjugate of a number and a number have the same modulus. So yeah, this is just done. This is equal to now take the limit as delta z goes to 0, and you get ux of xy plus I times vx of xy. And that's, as we know from the previous computation, that's an expression for f prime. Or more likely, we can say that this converges. So f prime of z exists. And this is just replicating the formula that we got for f prime in the previous direction of the proof. So essentially, it sort of feels like kind of chicanery, right? Like, what have we done? Really, all we used was basic two-variable, not even two-variable calculus. This is essentially just one-variable calculus because we've restricted to the x direction and y direction to use the mean value theorem, continuity, which is a calculus 1 idea, and then just a bunch of algebra. And all the Cauchy-Riemann equations let us do was resort this thing algebraically into pieces that exist. That's it. So what have we concluded here? We conclude that if ux is equal to vy and uy is equal to minus vx, then assuming all hypotheses, f is complex differentiable. All right. And that, I guess the takeaway here one of the takeaways here is that complex analysis is very, very, very rigid. And by rigid, what I mean is small assumptions about the behavior of a function turn out to have large consequences. So the assumption that a single derivative exists implies that infinite derivatives exist in the complex differentiable setting. The solution to pieces of functions being solutions to a very simple set of differential equations involving first partials forces functions to be once differentiable and thus analytic. And all of it basically just follows from baby calculus, right? So see you guys next time.